Okay, so hi everyone. So welcome to today's class. I think you already know Dr. Aziz is on travel, and so he's actually attending a conference in Arizona. So that's why I'm here. I will be taking this today's class. My name is Shamiul, and I'm a PhD student in Dr. Aziz's group. And in today's class, we will talk about this another semiconductor device named bipolar junction transistor, most famously known as BJT. So this is like a semiconductor device like the PN junction. So I know you already have learned a lot about PN junction, right? So you know the working principle and the device physics for PN junction. So those concepts will be useful when we will discuss this new device today. And we'll always, many times we will compare with that PN junction to understand this new device, okay? So if we compare with PN junction again, so in PN junction, we had two regions, right? One P-type and another N-type material connected side by side, and that was those two are creating the junction. But here in BJT, instead of two regions, we have three regions. We can have these two possible combinations, like you can see in the first one NPN, and the second one you can see this one PNP, right? So these are the two possible combinations when we put three N or P type materials side by side. Can we have any other combinations? Except these two, can you have any other combinations? So you might think of like this, like we can have N, N, and P, right? Or something like P, P, N, right? These are also like, here we are also using three N or P type regions, and we are putting them side by side, right? But the problem is here, if you put the same material side by side, they will actually merge with each other, right? Because, and they will behave as one N-type material in the first case. And in the second case, this two P-type material will merge with each other, and they will behave as one P-type material. So instead of having three separate regions, we will end up having one P and one N, which is exactly like the PN junction, right? So we need to separate the two same type of materials here. So for that, what we need to do, we can have like N-type material on the two sides, but in between, we must have the other type, P. Or if we put P-type materials on the two sides, then we must have the other one, which is N-type material in between, right? Otherwise, again, if we put same type material side by side, they will merge and they will have become the one, right? So we need to separate the same type of materials with the other type. So that's why we can, these are the only two possible combination we can have, like NPN and the PNP. These are the two possible combination, and they are known as NPN BJT and PNP BJT. Okay, these are their names. So again, here we have three regions. That means we will have three terminals for this device, and they are known as emitter, base, and collector. And you can imagine by the name. So this emitter here will emit something, right? So this might emit electrons or holes based on the region, right? If we consider this is an N-type material behaving as emitter, it will obviously emit some electrons, because in N-type we have more number of electrons. You already know this, right? And again, if we have a P-type emitter, then we will have more number of holes. So that will emit holes to the other regions of this device. So, and as you can imagine by the name collector, so this collector will actually collect those emitted electrons or holes. Okay, and base is in between. This base will actually help this emission and this collection. So this transfer of electrons or holes from emitter to the collector. So base will help in that process. Okay, so these are the three terminals, emitter, base, and collector. And how can we identify like which one is emitter, which one is base, and which one is collector? Okay, so the region in middle, which always be our, will always be the base. Okay, so for NPN, this P-type material will be the base, and PNP, this N-type material, which is in middle, will be the base. Now, now the thing is like which one will be the emitter and which one will be the collector, because on the either side we have the same type of material. Like for NPN, we have N-type material, For PNP, we have the same type, P type material. But the question is, which one will be the emitter, which one will be the collector? So for that, we will have to look at this doping concentration of each regions here. So you see, we have some additional notations here, plus, 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 which are new, I guess. Like in PN junction, we didn't have that, right? We only had like a normal P type and N type material. So these plus, plus, and plus notations are actually representing the relative doping concentration. Okay, so if you look at this N region here, this is like the normal N-type material we used in PN junction. But if you look at this P plus, so this plus represents it has higher doping concentration than this N-type material. Now, if you go to this N plus plus, this means this region will have even higher doping concentration. Okay, so among these three regions, this N plus plus region will have the highest doping concentration, and this N region will have the lowest doping concentration. So now the region that has the highest doping will always be the emitter, because we want the emitter to emit something. So that must have the highest amount of majority carrier or minority carrier, right? So we want more carrier in that region, in the emitter region. That's why the region that has the highest doping will be the emitter, and the other one, which has the lowest doping, will be the collector. Okay. So similarly for PNP, this P plus plus will have the highest doping. So this will be our emitter, and this P region will have the lowest amount of doping. So these will be our collector. Okay. And these two you see here, these are the circuit symbols for this NPN and PNP transistor. And when you take the circuits course, like 336 electronic circuits course, where you will learn about BJT based circuits, or also Dr. Rajesh might teach you some BJT based circuits in the next lectures. There you will see these symbols. You will not see these structures anymore. You will only see these two symbols for NPN and PNP BJT. And you can see they are pretty similar. There is only one difference, which is the direction of this arrow. Right. So for NPN, we have the arrow directing outwards from the device, and in PNP, we have the arrow directing inwards the device. So this is the only difference. And from this, you'll have to identify which one is NPN and which one is PNP when you design circuits. Okay. And we'll also talk about the reasons, right? Why we are showing outward direction and inward direction for NPN and PNP when we will talk about the working principle of the device. Okay. So these will be clear there. And another thing from this slide to remember is this. So I can remove this. So if you look at this structure, you can see that the width of the base here. So this is our base region. So width of the base is actually smaller than all the other regions, right? So although the structures are not drawn to scale, but you can still notice that, right? The width of base is much thinner than the other two regions. And this is done to improve the performance. Okay, improve the performance of the device. And we'll also talk about this in detail in the next slides. Okay, so and here there is a restriction when we choose the width of the base. Here, this must be less than the minority carrier diffusion length. So are you familiar with the diffusion length term? Have you heard that during the PN junction? So what is that? Can any one of you tell me? So what do you mean by this diffusion length? Forget about the minority carrier now, just diffusion length. What does that mean? So we know, like when we don't have any bias in the PN junction. So if we go to the next slide, so in PN junction, here we have P region and N region. So for P, we have more number of holes that we represent with the plus sign. And in N region, we have more number of electrons that we represent with the negative sign, right? So when we don't have any bias at the zero bias condition, what happens? These electrons actually diffuse because there are more density of electrons in the N side, right? So electrons will diffuse from N to P type. Are you familiar with this, right? So electrons will diffuse from this side to this side, and similarly holes will diffuse. And that's why we have this depletion region. We call that, right? The barrier is that forms, named the depletion region. So now when this electron diffuses from this region to this region, they can travel very easily without any barrier, but they can also collide with other electrons, right? They can collide with other electrons and they can get stopped. And also another thing can happen, which is the recombination. You are also familiar with that, I guess. Like some electrons may like recombine with the holes, which is the exactly opposite carrier, right? So they can recombine and they can get neutralized, we call that. So diffusion is length is that length which a carrier can travel before getting stopped due to collision or before getting neutralized due to recombination. Okay, so if they travel this amount of length before getting stopped, we call this length is the diffusion length. Like the length that a carrier can diffuse freely before getting stopped or before getting recombined. Okay, is it clear? So this is called the diffusion length. Okay, so here minority carrier diffusion length means the diffusion length of the minority carrier. So if we consider the n-type material, there our minority carrier is hole. So we are more concerned about the diffusion length of the hole instead of electrons. Okay, so you'll see that when we talk about the working principle of this device, you see that the current that will flow through each terminal of this device that flows due to the flow of minority carrier of each regions. That's why we are more concerned about this minority carrier diffusion length instead of majority carrier. Okay. So here, these two are the cross sections of fabricated BJTs, which are like practical device. And you can see that these structures are much more complex than the ones we saw in the last slide, right? So in the last slide, we just those are just illustration of the structure, and we could draw like emitter, base, and collector. Those are the three terminals, right? So we could draw them anywhere we wanted, right? But when we make this device in hardware, like fabricate them, we don't have that freedom of having terminal in anywhere we want. Okay, so like when we make this device, we will have to create contacts. We call them contacts. So each contact will be the terminal here, right? So for each terminal, we'll have to create contacts, and the restriction here is that we can only make contacts on the surface of the device, because after fabrication, when we will like perform the measurement with that device, we can access those contacts and we can apply voltage or measure current. Okay, so that's the measurement process. So that's why we need to make those contacts on the surface only. And when we make those contacts, we use metal layers. We don't use semiconductor anymore. So we use normal metal layers. And you'll learn about this more when you take any VLSI course like 433. So there you will learn making those layouts or designs using those metal and other semiconductor layers. So here you can see that we can only have one metal layers, and we can only create the contacts on the surface. You see, these are our contacts: base, emitter, and collector, and all of those are made on the surface. That's why we have this much more complex structure than the ones we saw in the last slide. Okay, so that's the main reason of having this complex structure. There are other reasons. For example, here you can see we have an additional layer. We call this buried layer. So this is not related to the basic working principle of the device, but we use this to improve the performance. For example, this is used to reduce the resistance of the semiconductor that we will be using in this device. So if you have more semiconductor resistance, that will like flow lower amount of current. We know that, right? So we want more current through the device. That's why we need to reduce that resistance. And for that, we use this highly doped N++ layer as the buried layer here. So, and another thing we need to look at here, you see there are two P+ region, which is not again part of the device, because in our device, this is the NPN device. Here we only have one N, two N and one P layers, right? So these P+ layers are not part of the device. So why are they here? So the thing is, like when you make circuits with NPN or PNP transistors, you don't use only one NPN, right? You might need more than one NPN transistor, and you might need to fabricate like multiple NPN transistors side by side, right? So when you put them side by side, as I already explained, these N regions, if they are put side by side, they will again merge, right? So these two devices will not be isolated. They will be, some parts of those devices will combine together, right? So that's why we need to use this isolation layer here. So what happens, like if we have two NPN transistors side by side, we can use one P+ region in between, because this P+, as I explained, like to separate same type of materials, we need to put something which is on the other side, like which is the other type of material. Like so, if you want to separate to N-type material, we must put some P-type material in between. So to separate to NPN transistor, we need to use P+ layers, which are here. You can see that these are the isolation layer. Similarly, if you want to separate PNP transistors, neighboring PNP transistors, then you will have to put N plus layer here as the isolation layer. Okay. So this, and here you can see in the second figure, this is another variation of the fabricated device. Here, this is like there are different fabrication steps, and you can see this is one of the improved version. So this is the very conventional version, and this is very improved version. Here you can see that we don't use P plus layers anymore. We use oxide, right? You know that oxides are insulator, so they cannot conduct. So even if we have two neighboring NPN transistors, if we place some oxides in between, they will prevent the current flow from NPN to NPN, another NPN. So they will act as the isolation layer, right? So, and this oxide actually solves another challenge. So if we talk about like this, so we only considered like isolating NPN and NPN, right? By using P plus, okay? So now if we have one NPN and another PNP, now what should we put here to isolate these two transistors? Can you use P plus? So if you use P plus, this P will merge together with this P, right? And if we N, that N will merge together with this N, right? So using these isolation layers that we have talked about, like using P plus or N plus material, they can only separate same type of transistors. Like if we have only NPN beside NPN, then we can use P plus. If we have only PNP and PNP, then we can use N plus layer. But if we have both types, like NPN, then PNP, we cannot use this like this way, right? So that's why this use of these oxide materials are more advantageous or more useful actually. So you can separate any type of transistors, neighboring transistors, by using any oxide material here. So, and here in this slide, we are seeing the doping profile for this device. I think you have already seen this type of doping profile for PN junction, right? So when we make the PN junction, we dope one side as P type material by using acceptor atoms, right? So for P type, we need to dope with acceptor atoms, with the trivalent materials. And for N type materials, we need to use donor atoms, which will create free electrons, which are the pentavalent atoms. So this ND actually here, the number of donors, and NA is the number of acceptors, right? So you already know this. So here, this is the doping profile of this BJT. And in the y-axis here, we are showing the difference between number of donors and number of acceptors. So in the first one, we have this N++ region, right? Where we'll have more number of donors or more number of acceptors. So in the first layer, what we will have? Will we have like more number of donors or more number of acceptors? N region, right? So N type material will obviously have more number of donors, right? That's why we are seeing some positive number here, because here we will have more number of donors than acceptors. And also we have this plus, that means it's highly doped. That's why we are seeing this highest number here. You see, if you compare these other two regions, this number is highest because this is the highest doped region in this device here, right? And then you have this P plus region where again we will have more number of acceptors because this is P type material. That's why we are seeing negative number here, because now this acceptor is more than the number of donors here. So we'll have some negative number, but not as high as the first one, because this is less doped compared to the first region. And then we have again another N region where we'll have more number of donors, but you see this is the lowest number we are getting because this is the lowest dope region in the device, right? So this is the doping profile. And here we need to note one thing, which is we have assumed that the device is uniformly doped. So what do we mean by uniformly doped is that when we dope one region, we assume that the doping concentration through the whole region is uniform, like same. That's difficult to do in practical life, but for the for the easiness of calculation or also like derivating the physics, we assume this uniformly doped condition. Okay, that's why we see this is constant line here, right? So for the emitter, this is our emitter, this is our base, and this is our collector. So for emitter region, you can see that for the whole region, we have the same number of doping concentration because we assume that these are uniformly doped. But in practical life, we will have some gradient. So these will change, maybe less, more, something like that. So you'll have some zigzag in terms of doping for doping concentration instead of having this constant line. Okay, so if you have assume the uniformly doped, then you will have this constant line. And I think in this course you will also use this ticket centers. You had one lecture on that, right? Ticket centers tool. So when you use that, you will use that tool. There you will be able to choose this doping like type. There you have like Gaussian doping, you have uniform doping, you have all those like different variants of doping. So you can do that in simulation, but in practical life, you have like much less control actually on the type of doping you do. And this here actually this mentions the typical number of doping. As I mentioned, like this emitter will have the highest amount of doping and the collector will have the lowest amount of doping, right? So these are the typical numbers that are used. For emitter, we use 10 to the power 19. For base, we use 10 to the power 17. And for the collector, we use 10 to the power 15. These are typical numbers here. So now I will talk about the working principle of the device here. So again, before going to this device, we will first like remember the concept of PN junction, right? So in our PN junction, we had again one P-type material and one N-type material, right? And when we biased this PN junction, we had how many combinations did we have? How many modes did we have for the PN junction? 3. So mainly 2, right? If we ignore the zero bias, because when we bias, we only have 2 conditions, either forward bias or reverse bias. So we know all the right. If we connect positive terminal to the P and negative terminal to the N, that is our forward. And if we connect in opposite direction, like negative with P and positive with N, there will be our reverse direction, right? So we know that. But now here, if you look at this structure, so we can draw it here again. So N, P, N. So if you look at this structure, you can see that whenever one N-type material connects with another P-type material, that's actually one PN junction. So this is actually our one PN junction here. And similarly, this is another PN junction here. So in this BZT, we actually have 2 PN junctions, right? So, and we know this is our emitter, this is our base, and this is our collector. So this PN junction here, that is, we have between emitter and base, we call that EB junction. EB junction or B junction, they are exchangeable. And similarly here, this PN junction is known as the BC junction or CB junction. Okay, so in this BZT, we actually have 2 PN junctions. And we know for each of the PN junctions, we can have 2 combinations, 2 conditions, right? For either forward or reverse. So if we think about this NPN transistor here, we have 2 PN junctions, EB and BC junction. Let's write them. So EB and BC junction. So you have these 2 junctions, and for each of the junction, you have 2 different biasing conditions, right? So how many combinations can we have here? 2 for each, and we have 2 junctions. So this should be straightforward. We should have 4 different combinations, right? Where we can write them actually. So where both of them can be reverse biased, right? The EB junction can be forward biased, BC junction can be reverse biased. We can have the opposite scenario where EB junction is reversed, BC junction is forward, and both of them can also be in forward biased. So these are the 4 combinations that we can have, right? So these are actually the 4 modes of operation for BZT here. So when we have both of these junction as reverse biased, we call that cutoff mode. Then when we have EB junction forward and BC junction reverse, we call that a forward active mode. And when it's the exactly opposite scenario where EB junction is reverse and BC junction is forward, we call that inverse active mode. And when both of them are forward, we call that the saturation mode. So these are the 4 modes of operation for this BZT device. And in today's class, we'll only talk about this forward active mode because cutoff is nothing, like both of them are reverse, so nothing exciting happens here. So we'll talk about this forward active mode, and we'll only consider the NPN junction for this, because the discussion for PNP will be exactly similar here. And also, like if we can learn this forward active mode properly, then we can actually like understand the other modes like inverse active, which is the exactly opposite thing, and the saturation mode more easily. That will be more clear, is easier to us. And I think in the next class you will learn about all those other modes. But here we'll only learn about this forward active mode, where, as I have explained, this EB junction will be forward biased and this BC junction will be reverse biased here. This is the forward active mode here. And you can see that if you look at this biasing condition, to make this EB junction forward, we are connecting negative to the N-type material and positive to the P-type material. Similarly, to make this reverse, we are connecting positive terminal to this N-type material and negative terminal to this P-type material. So this is our biasing to make sure that this EB junction is forward and BC junction is reverse. Okay, so this is our forward active mode. So we'll first look at the band diagram here. So I think you already did this for PN junction, where we had two layers, two regions. But if we look at the band diagram at zero bias condition, right? So if you have zero bias, we know in the equilibrium condition, the Fermi level of the whole device should be same in the equilibrium condition, right? So we should have one Fermi level for the whole device. Now, at the very left, we have these N++ regions, right? So when you have N-type material, we know that the conduction band will be now much closer to the Fermi level, and valence band will be further away from the Fermi level. Then we have this P+ regions, where again we know this valence band will be now be the closest one to Fermi level, and conduction band will be further away. Similarly, then we have N-type material, where we have this conduction band closer to the Fermi level and valence band to the further away from the Fermi level, right? So we know all of this. Now, when we make this device, when we create interface between these three separate regions, what will happen is all the conduction band will now be connected and all the valence band will now be connected. So if you look at this here, we will get this type of band diagram at zero bias condition, right? And we also know about this barrier, right? This is because of the depletion region here. So in PN junction, if you remember, we had the same type of barrier, right? We call that built-in potential. Do you remember that? Do you remember that term? So we had that built-in potential, which we had to break to make any current flow, right? So we had to apply something greater than 0.7 volt, right? So we had that built-in potential. So this barrier is actually this built-in potential. And you also know that when we bias a PN junction in forward bias condition, does this barrier decrease or increase? In forward bias condition, will this barrier increase or decrease? Decrease, because that will be easier for the current flow, right? So as you can see here, this is with considering the biasing conditions, and you can see when we make this EB junction forward, this barrier here between the E and B, emitter and base, that actually reduces, right? And that makes the that makes it easier for the electrons to move from emitter to the base. And you can see that this B and C, like junction between base and collector, is reverse biased. So reverse bias should increase this barrier, right? That's why these two, like conduction band and valence band for this N region, are actually getting lower, because that is actually increasing the barrier. We know that like reverse voltage is getting added to the built-in potential VBI plus R. So the barrier will now be increased for the reverse bias condition. And if this is reverse bias condition, you know that like if electrons are here because of the forward bias condition, they will have more motivation now to go there, because this is the lowest energy state. Okay, so this reverse bias condition will actually make it more easier for the electrons to go to the collector from the base. So you can see that now the whole process from emitter to collector, if we think about the whole process, first, due to the forward bias condition, the electrons will move from emitter to the base, and then due to the reverse bias condition in the BC junction, the electrons will now go to the collector. Okay, so we are having the same thing like the PN junction. Electrons are flowing from emitter to collector, right? So the question is, why do we need this base here? We could just only have emitter and collector, and we could like create the flow of electrons from emitter to collector, right? So why do we need the base here? the thing is like, if you again think about the PN junction, there we only had on and off, right? In forward bias, you have current flow. In reverse bias, you don't have any current flow. So on and off. Can you control that on and off condition? There were no any other terminals. We only had two terminals. We can have either forward or reverse bias condition, right? But due to having this base terminal here, we can actually control this flow of electron. We can control whether the electrons will flow from emitter to collector or not, right? So we have two controls here. The first one is again the biasing here, like the forward reverse that we think of, like forward active, inverse active mode. And we also have this bias base terminal here, where we can apply voltage to control. Even if they are forward biased, we can control that the electrons will not flow, right? So this base actually giving us this third terminal, like the controlling terminal here. And when you will again take the course, like circuits course, you will understand like what's the advantage of having this third terminal, right? So obviously the PN junction diode was the very first device. And then this NPN junction was like invented. And that was actually a revolution. Like when this NPN or BJT actually invented, it was the revolution. And if you look at the electronic products of 70s, 80s, there we had this BJT. But later, people invented MOSFET, which you will also learn in this course. So MOSFET, which has like mass superior characteristics than BJT. So that actually replaced BJT from the electronic products. And now we only have MOSFET and their variants, not BJT anymore. But like the major reason for this, like the invention of BJT was that third terminal. Like when you learn about the logic circuits, like how to design those NOT and OR gates, you will see that this third terminal is always the most important terminal. We need to have that control in the circuit design. Okay, so this base is very important here. So now, before going to this figure, which will explain the working principle of this device, I will first explain the working principle from the very high level without using any device physics. Okay, so that will again, I think, be more convenient to understand this device here. So let's erase this. So let's draw the structure again. We have this emitter, base, and collector. So this is our N, P, and these are N region. So this is emitter, this is base, this is collector. So this is our forward, this junction is forward, and this junction is reverse, right? So before biasing, we will have like we remember that we will have the diffusion of carriers, right? So when we don't have any bias, there are more number of electrons. So some electrons will diffuse here, some holes will diffuse here. So we will have again that depletion region for each of this junction. Okay, so that's true for any PN junction. Whenever we connect any N-type material with P-type material, we have a depletion layer in the connection point or in the interface. Okay, so we'll have the depletion layer here. Now, when we make this junction forward by applying that bias, what will happen is it will drive these electrons from here to the base side, because that's the activity of forward bias, right? So we want the flow of carriers. So due to the forward bias, electrons will flow from here emitter to the base, and also here we have more number of holes, so that will drive holes to flow from base to emitter, right? Now here, when the electrons come here, here we have huge number of holes, right? The P plus region, if you remember. And these electrons from the emitter, when they come here, they will recombine with holes, right? When you have more number of holes, electrons are coming, they will recombine and get neutralized. So some of the electrons that are coming from the emitter will get lost here in the base region. So we can actually show this type of flow. Some electrons are coming here in the base region, and some of them are getting lost in the base region. And then rest of the electrons will actually diffuse to the collector side, because there we have the reverse biased condition. And there we have like plus polarity, which will attract the electrons as well. So rest of the electrons will actually flow to the collector. Now you see, again here, remember the concept of diffusion length. that I discussed in the very first slide. So if we have much wider base region here, what will happen? That might be greater than the diffusion length of some carriers, right? So some electrons might get stopped or get recombined, like most of the electrons might get like lost due to the width, because the width will be greater than the diffusion length, right? So if you remember this, so this is our width. If the diffusion length is this much, right? So most of the electrons will get lost after traveling this point. So there will be very less amount of electrons that can go to the collector. But if we have, this is our diffusion length. So if we have a base which has like smaller width than the diffusion length, then most of the electrons will not get lost. They will go to the collector. Some of them will get lost due to the collision and other effects, right? So that's why, remember that, that's why we need to make the width of the base smaller than the minority carrier diffusion length here, right? Because in the p-type, election is the minority carrier. So we are more concerned about the electrons going from emitter to the collector here. So you understand that right now, why we need to make the width of the base smaller than the diffusion length. Otherwise, most of the electrons would get lost, and we would get like less amount of electrons in the collector. Okay. So now, if we look at the current flow now, so here, if you look at the emitter, there are some electrons flowing from emitter to base. So the current will flow to the opposite direction, right? The flow of current is opposite to the direction of electrons. We know that, right? So the emitter current, the direction of the emitter current will be this. Is that correct? So this will be our emitter current, right? So here again, in the base, some electrons are recombined, right? So are getting recombined with holes, and they are being lost, as I mentioned, right? So some electrons will flow this way, and the other electrons will go to the collector. So if we look at the base now, this is the direction of electron flow. So the current will flow to the opposite direction. So these will be our IB, base current direction. And again, here the electrons are flowing from base to collector. So the current will flow to the opposite direction. So these will be our IC, direction of IC, right? So now if we again draw the circuit symbol, which is much simpler than the structure. So this is our base, this is our collector, this is our emitter. So now if you compare this structure with the symbol, you can see that the emitter current is actually going outwards from the device. That's why we had this arrow directing outwards from the device. In the very first slide, you remember that, right? For NPN, we had this outward. And if we do the same thing, the current flow and electron flow for PNP transistor, and we will see that the direction of emitter current will actually be towards the inside of the device. That's why we had that inward directing arrow for PNP. Okay. So, and if you again look at this, and if you think of from the very high level, we have some electrons flow from emitter, which is creating this emitter current. Some of that electrons are getting lost in the base, which is creating the base current, and the rest of the electrons are going to the collector, which is creating the collector current, right? So we can think of in this way that the base current and collector current are actually two components of the emitter current. Is that correct? We had one emitter current which is getting divided into two portions. Some of them are getting recombined, creating the base current, and the other, like the flow that I drew. So we had total thing here, emitter current, then some of them was going to base and some of them are going to collector. So if we again think of the Kirchhoff's current law, KCL, we can write that emitter current will always be equal to the sum of base current and collector current. And that's true for any BJT, for NPN and PNP. These will always be true. The emitter current will always be equal to the summation of base current and collector current. Okay, so now let's go to the physics. Like, let's try to explain the same behavior using the physics, which is the purpose of this course actually. So that's the high level understanding I have discussed. Now I'll talk about the physics. So as I mentioned here, we are more concerned about the minority carrier. That's why this figure here is showing the minority carrier distribution. Okay, so we'll go step by step. So first, let's talk about these two walls that we see. Can any of you tell me what are these? What are these two walls here? Sorry. Yes, you're correct. So these are the two depletion regions, right? As I mentioned, like whenever we have NP, PN or NP junctions, we will have depletion region. So here we have emitter base junction and we have base collector junction. So these are the two depletion regions for those two junctions. Now, can any of you tell me why emitter base junction is thinner and base collection depletion region is actually wider? Why? That's not related to the doping. That the doping concentration will be related to the concentration of electrons and holes, right? But the depletion region will depend, as I explained, depends on the biasing, right? So when you have forward bias, that typically reduces the barrier, like VVI minus VF, or the forward bias voltage, right? So the barrier between the like the built-in potential barrier that we have, which is due to the depletion region, that decreases, right, in the forward bias, and in the reverse bias that increases, and that should actually explain this thinner and wider depletion region. So when you have forward bias condition, the depletion region breaks, we cross the barrier, so it becomes thinner. And in the base collector PN junction, we have the reverse bias condition, right, for the forward active mode. If you remember, this junction is forward and this junction is reverse. That's why we are seeing wider depletion region in the BC junction, because that's reverse biased. Okay. Now, as I mentioned, we will mostly focus on the minority carrier. So if we look at the emitter side, which is an N-type material, right? So here our minority carrier is hole, right? And we know this notation, I guess, hole. So what does this notation mean? Do you know this? So you should have seen this in PN junction lecture, I guess. So here P means the number of holes, or doping concentration of holes. N means the region. So number of holes in the N region, 0 means the equilibrium condition, thermal equilibrium. So if we have thermal equilibrium condition without any biasing, we know that there is a formula, NP equal Ni square. We have the intrinsic concentration of carriers, which should be the multiplication of number of electrons and number of holes. We know that, right? So in the N-type region, which is emitter, we have more number of electrons, and we actually have the most number of electrons in the whole device, right? Because that's the highest doped. So if we have most number of electrons, we should have the lowest number of holes. That's what we see, like these dashed lines, 3 dashed lines are the equilibrium condition. So you see that in the emitter side, we have the lowest amount of holes, right? Now, if we go to the base region, which is P-type, here we'll have more number of holes, but less number of, so minority carrier will be electron. That's why you see this notation here, electron, number of electrons. On the P side, 0 means the equilibrium, okay? So here you can see that these are the number of, or the concentration of electrons in the equilibrium condition. And if you go to the collector side, which is N-type, here our minority carrier will be hole. So we'll have the same notation, Pn 0. And you can see this is the highest value because this region is the lowest doped among the 3 regions. So when you have the lowest dope, that means you have less number of electrons compared to other regions, less number of majority carrier actually compared to others. That's why we have highest number of minority carrier here. So I think we have understood this 3 dashed line so far, right? These are the equilibrium condition. Now, when we apply the bias, as I've already explained, so when we apply this bias to make this forward and make this reverse, what happens? This forward biasing actually drives some electrons from N to P, and also holes flow from P to N, right? So some holes will flow from base to the emitter. Is that correct? So due to the forward bias, hole will flow from base to the emitter. So as you can see here, and this hole will first gather close to the depletion region, then they will go further away, right? So if we look at this PN junction here, and if we look at this side of the PN junction, here we will have the most number of holes because there are already some holes in the N-type materials, minority carrier, and more holes are coming from the base due to the forward bias. So we will have more number of holes, and you can see here, we have the highest number of holes in the emitter side in the when we are the closest to the depletion region. And if we go further away from the depletion region, as we go further away, we will actually have reduced number of holes, and at the very end of the device, we will have the same number of holes that we had in the equilibrium condition. So did you understand this, or do you have any confusion? So if you have any questions or confusion, please feel free to ask me. I will explain that again. So yeah, so that's why we have this highest amount of holes close to the depletion region, and when you go further away from the depletion region, we have the lowest number of holes. Now, if we go to the base region here, so again here in the base region, we have electrons as minority carrier, and many electrons are coming from the emitter side, right, due to the forward bias. So here again, the number of electrons will be very high. That's what we are seeing. And again, if we look at the closest point of the depletion region, there we will have the highest concentration, and that will decrease if we go further away from the depletion region, right? So here you can see close to the depletion region, we have the highest number of electrons, and then as we go further away, that is decreasing. And you can see here, up to this point, this makes sense. If we go further away, it will decrease, and at some point, we will have the same number of minority carrier that we had in the equilibrium condition. But there is another effect, which is the reverse biased condition, right? So if we reverse bias, this will also attract some electrons. So that's why you can see that at some point, the electrons will also move from base to the collector due to the reverse bias condition, and that will keep decreasing. And at some point, it will become zero. Until it becomes zero, the diffusion or the attraction of the reverse bias voltage will keep happening. So electrons will keep flowing from base to the collector until it becomes zero. And that's what you can see here. It becomes zero. Okay. Now, if you go to the collector side, here we have minority carrier, hole as the minority carrier. So, and you can see there, like in the collector, we are having a flow of electrons, right? The electron is flowing from emitter through base. It is going to the collector. Now, when more number of electrons will be coming, that will actually replace the holes in this like depletion region, right? So it will first replace the holes from the depletion region, and then it will keep traveling. So if we look at the closest point of the depletion region, here we will have the lowest number of holes in the collector because electrons are coming and they are replacing holes, right? So, and if we go further away from the depletion region, this point, we will actually have an increased amount of holes in the collector. Okay? That's what explains this like trend of hole concentration in the collector region. Okay, so did you understand this minority carrier distribution in the emitter, base, and collector region? So if we don't understand this, we will have hard time to like understand the next things that we will be discussing. Okay, so okay, so we have already explained. Ignore this dashed line. Just look at the solid line. So we have explained these three solid lines: emitter, base, and collector. How we are getting this concentration for the minority carrier in each of these regions. Now, again, the flow of electrons here will be like, we will have some flow of electrons from emitter due to the forward bias condition that will first go to the base, and then the electrons will flow to the collector. So if we again think of an ideal condition where we can make the like the very best BJT, where our goal will be to take all the electrons coming from the emitter to the collector. No, we'll need to make sure no electrons are getting lost in the base. That's the very ideal condition, and that's what we are seeing here. And the solid line that we are seeing, that's due to that assumption. If we can make that ideal device where no electrons are getting lost, we will have complete flow of electron from emitter to collector, then we can have this type of solid line or linear decrement in the electron concentration in the base. But that's not the scenario. We know that, right? Some of the electrons will recombine or will get lost due to the collision. So we will always have less number of electrons in the base than this linear approximation, right? That's why like this dashed line is actually the actual or practical scenario where we'll have some recombination, some electrons will get lost in the base, and the rest of the electrons will flow to the collector. Okay, so from now on the next slide, we'll actually look more on this dashed line instead of the solid line. Solid line is the ideal case here. So as we mentioned, like in our device, we had 3 terminals, right? Emitter, base, and collector. And each terminals we have the current flow. If we can bias them properly, like in forward active mode that we are discussing here, we will have current flow, right? We have already discussed that emitter current will be equal to the summation of base current and collector current. So we will have emitter current, base current, and collector current. Now we'll look at each of these currents individually, and let's first talk about the collector current. So here in the collector current, we know that the base collector junction is reverse biased, right? So there we should not have any effect from that voltage that we are applying because that's reverse bias. So here what will happen, as I mentioned, like everything will start from the emitter because emitter is it will start the process, will emit the electrons. So this will emit electrons, some electrons will get lost, then the other electrons will flow to the collector. Now, if this junction is reverse biased, how will that electron flow? So if you remember, I think you have already learned the drift current and diffusion current, right? Those are the only 2 current types you can have in a device, like drift current due to the voltage, like applied voltage forward bias condition, and diffusion current is due to the difference in density, right? So you have drift current and diffusion current. Now here, as I've explained, like this junction is reverse biased. The voltage does not have any effect on the current. So we don't have any drift current here. So the only type of current that we will have here is the diffusion current, because if you look at this, more number of electrons are coming here, and here we will have a huge number of electrons, more density of electrons here than the collector. So the electrons will naturally diffuse to the collector. So here we will have only the diffusion current, and you know that this is the equation of the diffusion current here. So you know E is the charge of electron, Dn is the diffusion coefficient, right? And that's related to the material. Diffusion coefficient represents how well carriers can diffuse through that material. So for a material, it's actually constant. If you use different material, that will have another diffusion coefficient value. And then we have this area here. So if we think about the total current, we should also use area. But if we use current density, then we don't need to consider this area, right? We can only have diffusion coefficient and the derivative term, right? So again, if you look at this here, we are using the area of emitter-base junction. But we are talking about collector current, but we are considering the emitter-base junction because, as I mentioned, the whole process is starting there. How many electrons are diffusing to the collector, that will depend on how many electrons are getting emitted from the emitter. So the voltage that we're applying between this emitter-base junction, that's important. And also the area of the depletion region, emitter-base junction region, that is also important because that will determine how many electrons are getting pushed into the base, and then it will eventually diffuse to the collector. So that's why we are considering this area of the emitter-base junction here, not the base collector junction. Now, if we look at this derivative term, we can have, this is the slope of this curve, right? The first derivation is always the slope of the curve. So we can calculate the slope like this. We can divide the difference between 2 y coordinates by the difference in 2 x coordinates, right? That's the formula of the slope. That's what we are doing here. So when we have at this x equals 0 position, we have the highest amount of electrons, which is NV0. And when we go at the very end of the base, which is XB, width of base, there we have like 0, because that diminishes. All the electrons diffuse to the collector. So there we have N equals 0. And we are using that here, and we are getting this formula here, right? So now if you look at this, you can see that all of these terms are actually constant. So once you make the device, the area of the junction is constant, the width of the base is constant, and also when you select the material, the diffusion coefficient is constant, right? So all of these materials are constant. Only this voltage that you are applying to the emitter-base junction will be the only variable. Okay, so that's what, like here you can see that this equation can be simplified like this. We can convert all the constant into one constant, which is IS, and we can have this exponential term that is related to the emitter base voltage that you are applying here. Okay. Now, if we go to the emitter current now, so here, if you look at this emitter portion, here again, we know that we had a huge flow of electron from emitter to base. So that will create one like current component, right? So if electrons flow from emitter to base, the current will flow to the opposite direction. And this is our IE1. So this IE1 current is actually due to the flow of electron from the emitter to the base. And this is like simple, and that will obviously depend on the voltage that you are applying, because the larger the voltage we will apply, the more amount of electrons will flow, so more amount of current we will have. So this is the very straightforward equation. And then also when we make this EB junction forward, this will also have a flow of holes from the base to the emitter, right? Because that's the P type and emitter is the N type. So electrons will flow from N to P, which is the I1 current, and holes will flow from P to N, which is our another component named IE2, you can say. And this is related to the hole. Again, that will depend on the voltage that you are applying, right? That will actually drive the holes from P to N region. And this IS2 is actually a constant related to the hole now, not the electron here. So these are the two components of the emitter side, emitter current. And if we add them, we can get the total emitter current. And you can see that in both of the components, we have this exponential term, which depends on the emitter to base voltage, and we have a constant. Right? And if you remember the collector current equation, we also had the same type of a constant, then the exponential term of base emitter voltage, right? So now if we take a ratio between this collector and emitter current, we call this parameter common mode current gain, alpha. This is a very important parameter, again, for circuit design. We don't care, you might not care about when you learn the device, but when you will use this device to design different circuits like amplifier, BJT is heavily used in amplifier design. So when you design those amplifier circuit, this alpha parameter will be extremely crucial. Okay. And so if you again, if you consider the ideal condition where we wanted all the electrons coming from the emitter go to the collector. So that was the ideal condition, right? So if we have had that ideal condition, there, what would be the value of alpha? If all the electrons coming from the emitter go to the collector, so the emitter current and the collector current should be same, right? Should be equal, because the same amount of electrons flowing from emitter to base, and then there is no flow of holes because there is no recombination in the ideal condition. All the electrons are going to the collector. So the collector current and emitter current should be equal. So in ideal condition, we should actually have alpha equal 1. I think there is some typo here. So this should be like alpha equal 1. So that's the ideal condition. But here in our case, we don't have that. Some electrons will get lost. So the collector current will always be less than the emitter current, right? So the alpha, the value of alpha will always be less than 1. But it's very close to 1. It's typically greater than 0.9 and less than 1 in that range, actually. Because that's what we want to do. That's why we make the width of the base smaller, so that most of the electrons can go to the collector, right? So you know that everything makes sense. So if you make the width much smaller than the diffusion length, then you can make sure most of the electrons will go to the collector. You will have comparable amount of collector current to the emitter current. Then you will have very high value, very close to 1, value of alpha very close to 1, right? So that's actually our goal. And if you look at this curve, so this is nothing but the collector current in the y-axis and base collector voltage that we are applying to make that junction reverse biased in the x-axis. And as I mentioned, this voltage does not have any effect on the current, right? It's just there to make that junction reverse biased, nothing else. So that's why you see we are getting constant current that doesn't have any dependence on the voltage. Okay. So, and you can see that if we have higher emitter current, that means more number of electrons are flowing to the base, that will create more number of electrons coming to the collector. So we will also have more collector current. That's what you're seeing here. So IE2 is greater than IE1, IE3 is greater than the other two, IE4 is the greatest one here. And for the larger the emitter current will be, the larger the collector current will be. So that's what you can see here. And another use of this BJT is that you can see here, if you only look at the base collector junction, you can actually design a constant current source, right? The voltage does not have any effect. So if you, even if you change the voltage, until it's in the reverse bias condition, you should have like this type of constant current. So this BJT can also act as a constant current source due to this behavior here. Now I think this is the last slide where we'll talk about the base current here. In the base current, again, if we look at this base here, we have already talked about one component, which is the flow of holes, right? Due to the forward bias condition of these junctions, some holes will flow from base to emitter, which is the from P to N type material. So this component will be also be in the base current here, and that's our IBA, and you can see that this is our IE2, the same component of emitter current here, due to the flow of holes. And there will be another component which I have mentioned, like the recombination. Some electrons will be recombined with holes, and that will create some current. But that is always like mass is smaller, because that's what we are ensuring by making the width much thinner than the diffusion length. So we should have a negligible current, but some amount of current will be there. And that will again depend on this base emitter voltage. As you can see, the recombination current that you will get, it will also depend on the base emitter voltage, because this base emitter voltage will actually determine like the number of electrons coming to the base, right? So if you have more number of electrons, you have more probability, or probability of more number of electrons getting recombined, right? So this base emitter voltage will eventually determine the number of electrons that get recombined in the base region. So that's why this base recombination current will also depend on this same exponential term here. So again, if you add these two IBA and IB term, we will get the total base current. And both of these has this exponential relation with the base emitter voltage. Now, again, if we do the same thing, if we take the ratio between collector current and base current, this exponential term will be nullified with each other, right? And we'll have a ratio of two constant, right? And we have this parameter named beta parameter. This is again another. So for BJT, we have two parameters, alpha and beta, and these are two like important parameters. And if you will, like when you solve the math problems, we will not do that in this course. So when you will have some math problems in this device, you'll see that if you know the alpha and beta for a BJT, you can actually calculate all the currents. You can calculate emitter, base, and collector current if you know the alpha and beta parameters. So this, when you purchase a BJT actually, so the most you care about like these two parameters. So you want to know the value of alpha and beta, and if you know them, you can design any circuit with that device there. So you learn more about these two parameters in the next lecture, I think. And you see, and now just one last thing, can you tell me like what will be the range of beta here? Will that be less than 1 or some larger value? Just remember the concepts of collector current and base current we have talked about, right? So we had this equation, if you remember, IE equal IC plus IB, right? Emitter current will be equal to the addition of base current and collector current. And we know that most of the electrons go to the collector. So the collector current will always be much higher than the base current, because a small amount of electrons are getting recombined, right? Because most of the electrons are going to the collector. So that will be the larger component of current in this device. So emitter will be the largest because that's the addition of both components. Then IC will be the closer one to the emitter current, and base current will always be some very small amount. Okay? So that's why if we take this ratio between collector current and base current, the beta value typically is very larger, in the range of 100 actually. Right. So ideally, we want that. We want like the larger the value of beta is, the better the BJT is. If we have like a beta of 200 for a BJT and a beta of 100, the BJT with beta 200 is obviously better than the like BJT with 100, because there we'll have more number of electrons going to the collector, which we want for the circuit design. Okay. So this alpha and beta are actually the performance parameters as well for this BJT device. If you know the alpha and beta, you know the formula of alpha and beta. Alpha is equal to IC by IE, beta is equal to IC by IB. And you know this formula, IE equal IC plus IB. So if you use these three equations, you can solve the device, and you can find out the value of all the different three currents, IB, IC, and IE in the DC condition, obviously. Okay, so you will be able to find out the operating points for this device, and you will be able to design any circuits with that. Okay, and yeah, I think that's all for today's class. And if you have any questions, please feel free to ask me. Do you have any questions?